All right. Hi. Hey. Hello. Happy Law of Sines 5.5. So, this is a pretty friendly, short, sweet section, but let's get into it. What is the law of sines? It states that the ratio of the sine of an angle to the length of its opposite side is the same for all three angles of any triangle. Well, what does that mean? I will say that sums down into this nice, neat blurb over here using our triangle to the right. I see that all of my angles are denoted with capital letters while all of the sides are denoted with lowercase letters. Another thing I noticed is that the sides in their angles directly across have the same letter. Directly across this angle A is side length lowercase a. Same thing with B and C. That's going to be very important because for the law of sines, back over here, I have the sine of some angle A over the opposite side A, little a, equals sine of some angle B over its opposite side B, equals sine of some angle C over its opposite side C. Opposite sides for this section are very, very important, and we'll look into what we can do with it. So when we are working with law of sines, we have a little bit of throwback to geometry in our alphabet soup, almost. AAS and ASA. If you remember from geometry, the A stands for angle and the S stands for side. We probably used them when we were talking about similarity between triangles. Which sets of angles and sides matching could determine similarity and which ones couldn't. In this case, it's mostly just letting us know what values that we know, which ones are we able to utilize to figure out for law of sines. So that first one, angle, side, is telling me that I know some angle. I know the direct next angle, whether I go counterclockwise or not, and I know the direct next side. Like I said, it doesn't matter if I go counterclockwise or clockwise, as long as I am keeping it consistent. For that second one, our ASA, I have an angle, I have the direct next side, and I have the direct next angle for angle, side, angle. These are going to be the two that we are absolutely guaranteed to be able to work with for law of sines. Other ones, sometimes we can't use law of sines at all, and sometimes we have a weird situation. We'll look at that. Just a reminder, if I'm given two angles and I really, really need the third, remember that the sum of the angles inside of our triangle add up to 180 degrees. So if I know this angle, and I want to figure out what this missing angle is, I can take these two and subtract them from 180. From there, we are able to solve for any of the remaining parts using our law of sines. And let's take a look at what that looks like. So I want to find the length of side x in our triangle. And for this one, I've been so kind as to have some dotted lines to help me figure out what sides correlate with which angles. But we know it's always what's opposite. I have an abridged version of our law of sines here because I only ever need two pairs. I need one pair that has complete with the angle and the side length both known, and I need my other pair to have at least one of the values known. In this case, I know what my angle is, but I'm trying to find that side length x. So let us do a little bit of filling in. I'm going to take the values that I don't know first. That's how I do it, but the order doesn't matter. So that sine of 40 degrees over the side length that corresponds to it, that's opposite, x, equals the sine of the other side length, of the other angle, 25 degrees, over the side length that corresponds, 4. I see a lot of people get really, really excited to do cross multiplication. And a lot of times I say, well, we can't actually cross multiply here. I know what you mean, but it's not actually cross multiplying. This is a case in which we can absolutely, absolutely cross multiply. I have two fractions separated by an equal sign. It's time to cross multiply.
And just a reminder that means I'm multiplying my denominator across the equal sign to get into the numerator of the other side, and vice versa. So what do I get? 4 times the sine of 40 degrees equals x times the sine of 25 degrees. If we remember from algebra, whenever I'm solving for something, in this case our side length x, I want to get my variable on one side and everything else on the other side. So I'm going to divide both of my sides by that sine 25 degrees. What do I get? X equals 4 sine 40 degrees over sine 25 degrees. Now that's great, but that doesn't really tell me much about a side length, right? I wouldn't say, oh, my shoe size is 4 sine 40 degrees over sine 25 degrees. It doesn't make sense. This is the time in which, if you haven't already get your calculator out, you might want to do that now, and make sure that it's in degree mode. If you'll notice, I'm using degrees, and I will exclusively be using degrees for this section and the next section. And if you have it in radians, you're just going to get messed up. I'll say with caution that we are just going to be throwing this into our calculator. But remember that calculators don't read the way that we do. They have a very specific way of reading order of operations, and this is where parentheses will absolutely save your life. Because if I just type in 4 sine of 40 degrees divided by sine 25 degrees, it's going to read 4 times the sine of 40 degrees divided by the sine of 25 degrees, which is a very, very weird thing. So how should you ideally put this in your calculator? Well, whenever you put a sine in your calculator or any of the trig functions, it automatically gives you parentheses for your angle measurements. Use those and close them. And then for our numerator, put your whole numerator in parentheses so that none of the parts are getting misplaced. It's optional to put your denominator in parentheses in this case. I don't have enough terms where it'd be tricky, but I would recommend parentheses. 4 sine of 40 degrees, close parentheses, divided by sine 25 degrees, close parentheses. All right, that's one example. Let's try another. One day I'll learn how to erase this. Okay, same idea, different triangle, different numbers. I want to find the side length of Q now. Same as before, I'm going to set up my angles, sines, sides, etc. I normally start with the side or with the pair that I'm missing something one. So I'd say, all right, 79 degrees is missing its side length. So I'd say sine of 79 degrees over Q equals the sine of my second pair, which is complete, sine of 40 degrees and 14. From here again, I'm going to do a nice cross multiply and get 14 times the sine of 79 degrees equals Q times the sine of 40 degrees. Divide both sides by that sine 40 degrees so I get just Q on its own. 14 sine 79 degrees all over sine 40 degrees. And you know what? As I'm writing this out, I realize I never actually gave you the answer for the last one. So I'm just going to do that now. For the last page, when I was solving for x, our value of x is going to be 6.1, which is actually very close to my shoe size. I was talking about that 4 sine 40 over sine of 25. Yeah, last slide was 6.1. Good to know. Same thing from here. I'm going to throw this into our calculator. I've given you the tools of how it should be put in syntax-wise, so I hope you got it. If I put that in, I should get that Q is 21.4. All right. I've had a few people in class ask how many decimal points should they go to. I would say, for me, as I am currently your teacher, I want just one decimal place, just to the 10th place, because I know that this side isn't exactly 21, since I have some sort of decimal, but so I wouldn't just give it a whole number, but I also don't want a long list of decimals. So I'm very happy with just 1 decimal place, please. All right. Beautiful. Okay. Solving a triangle if we're given 2 angles and a side. In chapter 4, we talked about solving triangles, and it's the same idea here, in which we're trying to find the values of all of our angles and all of the sides of our triangle. In chapter 4, we would have used probably sine, cosine, tangent, opposite over hypotenuse and all that stuff. We would have used Pythagorean theorem, a squared plus b squared equals c squared. But if you've noticed in our past 2 triangles, we haven't had a 90-degree. We haven't been working with right triangles. That's because for this section and the next section, we are working with general triangles, meaning we don't have right triangles. We don't have a hypotenuse. So if we don't have a hypotenuse and we don't have a right angle, we can't use any of our sine, cosine, and tangent as the way we know it, where it's that opposite over hypotenuse, because there is none. But we have been using our law of sines to do this, so I feel as though we are A-okay. Our goal is to find all of our angles and all of our sides. Our first step is always to draw it out. When you're drawing your triangle, what I am looking for is that 1, you have a triangle. I don't care if it's to scale. But 2, that you label your angles. I'm okay if you don't label your sides because I know that they're directly across from the angles and I can figure out, across from big A is going to be little a. But I absolutely am expecting to see your angles being labeled with their capital letters. All right, I'm given that angle A is 36 degrees, that angle B is 48 degrees, and that our little a is 8. I said that I'm solving, which means I'm going to be looking for angle C, our B value, the side, and our C value. Well, for angle C, that's pretty easy. I have 2 angles, and I know that for triangles, the sum of the angles always adds up to 180. So I can subtract 36 and 48 from 180 to get that. That's angle C is 96 degrees. Bam. From here, I get to continue doing some law of sines work. I have 1 absolutely complete pair with the angle of A and the side value of A. So that's our complete pair to work with. I'm going to start with B because it's next in the alphabet. So I'd probably say, all right, B has a angle value of 48 degrees. I'm looking for its B side value. I know my A has a 36 degree angle, and I know its side length is 8. So we've set up our law of sines. From here, we're going to do that cross multiplying again. We're going to get, if we cross multiply it out, that B equals 8 sine of 48 over 36 degrees over the sine of 36 degrees. Oh my goodness gracious. And if I throw that on my calculator, it's going to be 10.1. Cool. We have our value of B. Now, it might have been tempting to try and do all 3 of them at once. When we were given our law of sines, we saw that we had all 3 values at once. However, if I'm working with 2 side values that are unknown, and I throw them all into the law of sines at once, I'm going to have 2 variables bouncing about, and I'm never going to be able to actually solve for one of them. So always take 1 pair of complete angle and side, and 1 pair where you're missing one of them. All right, let's figure out what our side C is. I know that our angle is 96 degrees, and I'm solving for that side C. I could use my completed pair A that I was given, or my completed pair B. I like A. A's are nice. So I'd probably say sine of 36 degrees, our angle A, over its opposite side, 8. From here, I can do the same step of cross multiplying, dividing by a term. So I get that C is equal to 8 times sine of 96 degrees divided by the sine of 36 degrees, which, throwing that into our calculator, gets us 13.54. Bam! We have solved our triangle. We have all of our sides and all of our angles. Good job, team. All right, I'll give you a second. I'll let you pause if you really want to see it. Cool. So that's all been really nice, and that's what happens when we are given two angles and a side. But what happens if we're not? So we talk about the ambiguous case, or side-side angle. That's when we aren't given our happy two angles and a side. It's when we're only given two sides and an angle. Now, how we would go about solving these triangles depends on where the angle is located. If our angle is between two known sides, it's called a side angle side, and it uses the law of cosines, aka what we're doing tomorrow. So we ignore it until tomorrow. However, if our given angle is opposite one of the sides, then there might be 1, 2, or 0 triangles determined. What that would look like is if I have two sides and an angle that is opposite from one of them, side-side angle, that's when we can use our law of sines, but it'll be a little bit tricky, and that's okay. This is when we have to worry about the ambiguous case. Okay. Here's an example. I see that I have two sides, A, B, and one angle. So immediately I'm on alert. Am I going to be utilizing an ambiguous case? Am I going to have 1, 2, or no triangles? My first step, of course, is always to draw out my triangle. I'm given that the angle value of A is 26.3 degrees. The opposite side is 7, and the side opposite from angle B, which we don't know, is 6. If you read ahead, you'll probably see my little star note. If the side opposite the given angle is larger than the other given side, you're good. There's no ambiguity. Looking at our specific example, I see I will always have one pair of angles and sides that match up for our law of sines, law of cosines. Otherwise, we can't really do it. I see that 26.3 and its opposite side, 7. I want to focus, when I have side-side angle, on that side that is matched with an angle, 7. If the side that is matched is larger than the other side, or 6, then we're okay. We don't have to worry about the ambiguous case. We can solve this one exactly like normal. And what this one is going to look like, I just want to go through a little bit because we've been solving a lot for sides, but we haven't been solving very much for angles. So I wanted to talk about that just for a little bit. But it starts off the same setup. The sine of, I'll work with what I do know this time, 26.3 degrees, our A over our A side length, equals the sine of, well, we don't know B's angle. We've been calling it capital B, and I'm going to keep calling it capital B, over the piece of it that we do know, side 6. From here, so far, we can continue as normal, multiplying and cross-multiplying, getting everything on one side. So I get that the sine of B is going to be equal to 6 times the sine of 26.3 degrees over 7. Now, you might be really tempted to divide both sides by sine and say, oh, well, then I'll just get what B equals. But remember that sine, cosine, and tangent are functions. They need a variable in order to exist. If sine has, example, a 26.3 as its variable, it's a value now. But as I tell my students in class, sine without a variable is just sin. It's meaningless. So curb your temptation. Please don't divide both sides by sine. But there is another way in which we can figure out the value of an angle given the rest of the values. From chapter 4, you might have remembered taking the inverse of a function. You probably had to do it by hand, working with triangles, going back and forth, and all that fun stuff. I'll tell you it's easier with a triangle. If I take the inverse sine of the whole equation, what am I left with mathematically? Well, the inverse sine of sine is going to give me whatever angle is left, B. From here, I take the inverse sine of whatever's left on my right-hand side, 6 times the sine of 26.3 degrees over 7. You also might be tempted to say, oh, the signs over here will cancel out, but there's also a 6 and a 7 to account for, and we have to deal with those. So what do we do from here? We throw it in our calculator. If you're working with the TI-84 or really any version of TI, there will be a second button and the sign button. When you hit it in that order, second sign will give you the sign inverse. And from there, you're going to type in whatever is in our parentheses, just as before. Once again, make sure that you are in degrees mode, otherwise it'll give you a really weird, possibly negative value, and we know that angles and length can't be negative. Well, in this case, they can't be. So what do we get from there? We get that our angle B is 48 degrees. All right. So we know B is 48 degrees. That's telling I know from there that I can figure out C by subtracting 48 into 26.3 from 180. Oh, 48 degrees is the wrong one. Ignore that. So many numbers at any given time. 22.3 degrees. That sounds so much better. I know that I can figure out that last side by subtracting 22.3 and 26.3 from 180 to get a value of 131.4 degrees. So far, although I've gone through this case talking about the new thing of taking the inverse to figure out the sine, the actual angle, so far this case isn't that different. I know that I'm able to do the same thing and figure out our last side. Just letting you know that our side C is going to be 11.9. This is a pretty standard, very algebraic chapter. If you're still struggling with it and you want to see how I worked out that step, please email me or Mr. Pullman and I'll be so happy to show you. But a lot of it just keeps doing the same thing over and over. Okay. So we talked about one of our suspicious cases where I have side angle, but this one was fine because the side opposite our given angle was larger. So we're okay. The ambiguous case is specifically when the side across our given angle, our pair, this side is smaller than the other given side. So we are given a new triangle here. My first step is always to draw it out. Triangle A, B, C. I am given that angle A is 30 degrees. I am also given that the side across from it is 6 and that the side across from B is 7. Now we have something new because the side across from my angle, my side of pairs, 6 is smaller than my other given side, 7. In this case, I don't know if that 6 is going to be where it is or if it's going to be on this new line. It's a little bit difficult to draw on the smartboard, but since I only have one angle, I don't know the size of any of my other angles and if they'd be able to swing kind of back and forth. So we have to check both circumstances. We call our first idea case 1, in which we assume that our angle B, in this case, is acute. Case 1 is everyone's favorite because it's exactly what you think it's going to be like. We set our sines and cosines as we've been doing. Sine of 30 over 6 equals sine of B over 7. From there, I can take the inverse. I get that angle B is 35.7 degrees. From there, I could also figure out my angle C by subtracting 35.7 and 30 from 180 to get 114.3 degrees. And that's okay. That's pretty standard. From there, I'd be able to find my last side, side C, by using law of sines once again. And in that case, I'd get that our last side C is 10.9. Now, if we had a case 1, it follows that there would be a case 2. And if in case 1, we were assuming that angle B is acute, it also follows that in case 2, we might be assuming that angle B is obtuse. And how do we get a value of angle B that's obtuse? Well, we look back at case 1. In case 1, I see that I got angle B is 35.7 degrees. In order to have my second case in which angle B is obtuse, I'm going to take that angle that I originally found, that 35.7, and I'm going to subtract that from 180. There's a decimal there. When I subtract it from 180, I get that in this case, in this universe, the angle of B is 144.3 degrees. I have two values that I could have for B, and it's possible that both of these are right, but we have to check that, right? So how do we check it? We have our newly found angle, that 144.3 degrees, and we have the original angle that we're given, that 30 degrees. We check by adding them together. 30 plus 144.3 is going to be 174.3. I'm going to compare whatever number I got to 180. If we remember, 180 degrees is how many degrees there are in the inside of a triangle. If my newfound obtuse angle, 144.3, plus my original given angle, 30, was greater than 180, we have a broken triangle because two angles can't add up to 180 degrees in a triangle and one be mathematically legal, and also there'd be no room for the other angle. If that's the case, you're done. Ignore it. It can't happen. But in this case, 174.3 is close to 180, but it's not quite there, which means that this is a valid triangle. We're going to have two solutions. So what do we do from here? Well, we can still figure out our angle C by subtracting 174.3 from 180, and we would get 5.7 degrees for our angle C. We still have to find our side C. We can use our law of sines, and I'll let you do that and try and check yourself. You get 1.2. Someone asked in class, well, which one is your answer? Both of them are. If we're solving in the ambiguous case and we have that both of our cases work out, we don't know which triangle we're exactly given. It's kind of like when we take the square root of something and we have to say plus or minus, because we don't know if originally the number that was being squared was positive or negative, and so we have to account for both. In this case, we're not given enough information to know exactly what triangle it is, so we have to account for both possible triangles by having both of our answers. All right, I'll give you a second, put your pause. All right. Oh, what'd I do? Oh my golly. Okay, that was weird. Okay, not very much left. Okay, a lot of people ask in math, when will I ever use this? Which is a valid question. A lot of times, you probably won't use it in life, but you will use the critical thinking that you utilized for it. I will say that law of sines and law of cosines is one of the most useful aspects of trig in the real world, if you will. It's something that's used a lot for surveying and cartography when you're looking at land and creating maps. A lot of nautical and marine boat things. This is a pretty famous example where we have two rangers looking at a fire. And yeah, it's actually something that's really cool. I tell my students in person that I've taught outdoor education for a while, and I use trig to explain certain ideas. And I just think that's really cool. But what you might not think is cool is the idea of a word problem. And at first, when I see this one, I don't particularly love it, but I'll say that the math of it is very, very similar to what we've been doing. It's just the setting up. So let's look at it. Ranger Smurfy at Ranger Station A sees a fire in the direction of 32 degrees east of north. I think that's important. I'm going to underline it. Also, underline A. Ranger Rocky at Ranger Station B, which is 10 miles east of A, sees the same fire at a line of 48 degrees west of north. We want to find the distance from each ranger station to the fire, because depending on which ranger station is closer, the closer ranger is probably going to be the one to go first, while the second one calls for backup, firefighters, etc. This is a lot. Let's draw a triangle. What do I know? I know that I have someone in Ranger Station A. I know from that 10 miles east of A that B is going to be 10 miles east or to the right, although that's not how cardinal directions work, but for math, it's fine. 10 miles to the right or east of A. Cool. I have 2 points. Let's make them a triangle. All right. Handling Smurfy's line of direction towards the fire, 32 degrees east of north. I mentioned that for our triangles, we won't have right angles, but we will be utilizing right angles when it comes to situations like this. We're always able to be perpendicular to north, and so if she's spotting this fire 32 degrees east of north, this little angle in between where it's on the outside of our triangle, but it's still within that new 90 degrees we formed with our north line, is going to be our 32 degrees. That's cool, but it doesn't help us find our exact angle within the triangle. But if you remember the idea of complementary, or the fact that if I said that this is a right angle, I'm able to subtract that 32 degrees from 90 in order to get 58 degrees. Cool. We know one of our angles inside. We're going to be doing a similar thing for B. I draw a line north. However, Ranger Rocky is sighting at 48 degrees west of north. West is kind of left, to the left of north. This little pocket angle here is 48 degrees, and we can do the same thing to figure out that that triangle angle, subtracting from 90, is 42 degrees. From here, I have only one side length. I know my 10 miles. I want to probably figure out the angle for that so that I'm able to use that as one of my pairs. I see I have 58 degrees and 42 degrees within my triangle, and I know that all the angles in a triangle add up to 180. So if I subtract 58 and 42 from 180, my top angle is 80 degrees. What am I looking for from here? The 2 side lengths of our triangle, side A, side B, because I want to figure out who is closer. I'll help you set up and let you know. So I'll start with figuring out A, side A. So I'll take the sine of our A angle, 58 degrees, over our A side length, and set that equal to what I do know, our C. I will say the sine of 80 degrees over our 10 miles in between. I'll do some cross multiplying and get that A is equal to 10 times the sine of 58 degrees over the sine of 80 degrees. And when we go through that, we will get that our length here is 8.61 is 8.61, but I'm not quite satiated with it just being 8.61 because 8.61 what? 8.61 miles. All right, and that is our A value over here. Okay, so Ranger Rocky at Station B is 8.6 miles. Let's check out Ranger Smurfy at Ranger Station A. Same idea. I'm going to take what I don't know, what I know, figure it out. I'll take the sine 42 degrees over our missing side length B and set that equal to what I do know. I could use my values for C or for A. I normally stick with what I'm given originally, so I'd say the sine of 80 degrees over 10 miles and get that B is equal to 10 times the sine of 42 degrees over the sine of 80 degrees. And when I throw that into my calculator, I get that is 6.79, not nothing, but 6.9 miles. Doing all of this, I figure out that Ranger Smurfy is almost exactly 2 miles closer than Ranger Rocky is. So that means Smurfy is going to handle the fire first. I'll let you just take a second, pause if you need to, right? Okay. The last thing that we're going to talk about is the area of a side angle triangle. Now, you might be wondering, hey, we've only been talking about angle, angle, side, angle. We're going to talk about this one because it utilizes sine, and we're talking about sines in this chapter. We're used to our equation for the area of a triangle being 1/2 base times height. Well, some mathematicians were so kind to translate that into a new area formula that we can utilize if we are only given the two sides and an angle of a triangle, in which the area is 1/2 times a side, b another side, times sine of c, an angle. I have a nice triangle here. I'm going to label it just so I can remember which each of my pieces are. I know that capital C, and especially if I'm taking a sine of it, is definitely going to be an angle. It doesn't matter which of my sides I name as A and B, because they're being multiplied, and multiplication is commutative. From here, I can throw it in and say, okay, the area is 1/2 times our first side length times our second side length times the sine of our given angle. And when we multiply this all out, we're going to get 16.1. And just like before, it's not just 16.1. 16.1 what? For the other triangles that we've just been trying to find sides, we haven't used any units. But I see that I'm already given that it's millimeters. And especially for the fact that this is area, we always say that area is units squared, whether we know the units or not. In this case, we do. So 16.1 millimeters squared. I'll tell you that if you did a lot of extra work figuring out the base and or height, we would get the exact same result. But this is a way of figuring out the area if we're only given two sides and the included angle. All right, and that is all I have for you for 5.5, the law of sines. It's a nice, neat, chill, short, sweet chapter. So do your best and happy Monday.